Welcome to Academic Gain Tutorials. In today's class we are going to study product design considerations in casting. We are studying fundamentals of metal casting and metals for casting. We will cover all related topics one by one. Before starting, if you haven't subscribed to this channel yet, just click on subscribe and press the bell icon. Here, we come up with new videos on different subjects to make the academic studies easier for you. So, into the topic. Product design considerations in casting. In casting, certain guidelines should be followed to facilitate production of the part and avoid many of the defects discussed earlier. These include geometric simplicity, corners, section thicknesses, draft, use of cores, dimensional tolerance and surface finishes, and machining allowances. Number 1. Geometric simplicity. Simplifying the part design will improve its castability. Avoiding unnecessary complexities simplifies mold making, reduces the need for cores, and improves the strength of the casting. Number 2. Corners. Sharp corners and angles should be avoided, because they are sources of stress concentrations and may cause hot tearing and cracks in the casting. Generous fillets should be designed on inside corners, and sharp edges should be blended. Number 3. Section thicknesses should be uniform in order to avoid shrinkage cavities. Thicker sections create hot spots in the casting. Greater volume requires more time for solidification and cooling. These are likely locations of shrinkage cavities. In the figure A, we can see that a thick section at intersection can result in a shrinkage cavity. Solutions include the redesign to reduce thickness and use of a core. Number 4. Draft. Drafts are created to aid in removal of the part from the mold. The required draft need only be about 1 degree for sand casting, and 2 degree to 3 degree for permanent mold processes. In the figure A, we can see that a thick section at intersection can result in a shrinkage cavity. Solutions include the redesign to reduce thickness and use of a core. Number 5. Use of cores. Minor changes in part design can reduce the need for coring, as shown in these figures. In the figure A, we can see that a thick section at intersection can result in a shrinkage cavity. Solutions include the redesign to reduce thickness and use of a core. Number 6 is dimensional tolerance and surface finishes. First, let's study dimensional tolerance. Depending on the process, there are significant differences in the dimensional accuracies that can be achieved in castings. This table demonstrates typical dimensional tolerances for various casting processes and metals. Let's take this example. When we are casting using cast iron as the material, then for casting small parts, a tolerance of ±1 mm, or ±0.040 inches, is to be provided on all sides. Again, for casting large parts of the same material, a tolerance of ±1.5 mm, or ±0.060 inches, is to be provided on all sides. Similarly, for other metals also, we can find out the typical dimensional tolerances for various casting processes from this table. After dimensional tolerance comes surface finish. Typical surface roughness achieved in sand casting is around 6 micrometers. Similarly, poor finishes are obtained in shell molding, while plaster mold and investment casting produce much better roughness values of about 0.75 micrometers. Among the permanent mold processes, die casting is noted for good surface finishes at around 1 micrometer. Number 7. Machining allowances. Tolerances achievable in many casting processes are insufficient to meet functional needs in many applications. Sand casting is the worst, so machining is required. Therefore, additional material, called the machining allowance, is left on the casting for machining those surfaces where necessary. Typical machining allowances for sand castings range between 1.5 and 3 mm. So, we have studied product design considerations in casting. Thank you.
In this video we will discuss about casting defects. Before starting, let's see what is the definition of casting, or what is a casting process. Casting is a manufacturing process, in which a liquid material is poured into a mold, which contains a hollow cavity of the desired shape, and then allowed to solidify. The solidified part is known as a casting. What is casting defect? A casting defect is an undesired irregularity in a metal casting process. Some defects can be tolerated while others can be repaired, otherwise they must be eliminated. There are a lot of things that can go wrong with a casting, but it can be difficult to tell from the results what the problem is that caused it. It is best to avoid casting defects as much as possible. If the produced casting part is defective but can be tolerated, then it is machined as required, to make defective part usable, and on the other hand, if the part is unrepairable or not economical to repair, this kind of parts are usually considered as scrap, and will be thrown into the furnace to remelt and recast. Either way, the repairing or remelting incurs loss of resources, which otherwise can be used to produce more parts. This is a loss to the industry, thus casting defects are bad to the industry and should be avoided as much as possible. There are many types of casting defects, so they are broken down into 5 main categories. They are gas porosity, shrinkage, mold material, pouring metal, and metallurgical casting defects. They can be subdivided further. I will try to make it as simple as possible. Let's start with gas porosity. So, what is gas porosity? When cast metal solidifies in a mold, it can't hold as much gas as it does in liquid form, so it releases it. That is part of the reason molds are permeable, to allow gas to escape. Several factors can cause impermeability, which can result in gas bubbles getting trapped inside the metal. There are 3 types of casting defects related to gas porosity. They are pinholes, surface blowhole and open holes. Blowholes. Blowholes are larger holes that can appear in the inside of a cast piece. Invisible to the naked eye, interior blowholes are detectable by X-ray, harmonic, ultrasonic, or magnetic analysis. Open holes. A type of blowhole, open holes appear at the surface of part. These defects are caused by air getting trapped as metal is poured into the mold. How to prevent gas porosity? Avoid them by making sure the molding sand is dry and permeable. It should be noted that the coarser sand is, the more permeable it is. Even using sand that is too fine can prevent optimal permeability. Additionally, sand molds that have been rammed too much lose their permeability, so it's important not to overdo it. Use dry molds and cores, and be sure that there's enough venting in the molds to allow gases to escape. You should also use good melting practices by melting the material in a vacuum, around low solubility gases, or under a flux, which prevents air from touching the molten metal. Now let's discuss about the shrinkage defects. Shrinkage defects appear because metal alloys shrink as they cool. It is normal for an alloy piece to shrink as it solidifies. However, defects occur when the metal shrinks unevenly, causing it to either distort the shape of the final product or create interior holes. There are of 3 types: open shrinkage, closed shrinkage, and warping. Open shrinkage defects. Open shrinkage shows up on the surface of a cast product either as a dip or a hole. When metal shrinks unevenly, it draws air inside the mold in that area to create these types of defects. Closed shrinkage defects. Closed shrinkage appears in the form of holes inside of a casting, generally where a part of the liquid metal was hotter than the rest of the material. It can appear in macro or micro form. Micro shrinkage, also called shrinkage porosity, looks to the naked eye like jagged marks or lines. The holes, which look angular, can only be seen with a microscope. Warping. Warping can happen either during the metal solidification or afterward, changing the casting's dimensions and shape. This stresses the metal and causes curving, especially in large and flat sections of castings. How to prevent shrinkage defects. Problems with continuous flow at the right temperature can be lessened by ensuring a continuous, even supply of liquid metal into the molds. This can be accomplished by using a runner and gate system with risers to supply the molten metal. Additionally, molds can be given padding, which widens the ends of narrow pieces attached to thicker parts, as this helps ensure the thicker sections get enough liquid metal before the thin part solidifies. Some manufacturers also place cooling ribs, cooling coils, or chills inside the molds to disperse heat faster. Pouring the metal at a lower temperature may also help. Third main casting defect is mold material. As suggested by the name, mold material defects are caused by the mold material, but they can also be caused by mold design problems. This makes up the largest category of casting defects, with 7 basic types. They are cuts and washes, swells, drops, runout, fusion, metal penetration, and rat tails. How to prevent mold material defects. Ensuring molds receive enough ramming to hold the molten metal is an effective way to cut down on all of these problems, as well as making sure the metal being poured isn't too hot. 4 pouring metal defects. As opposed to many of the other defects, these defects appear when temperatures are too low during the pouring process. They fall into 3 categories. They are cold shot, cold shut, and misruns. How to prevent pouring metal defects. Pouring metal defects can, for the most part, be avoided by ensuring the molten metal stays warm enough to completely conform to the inside of the mold. The gating system can be redesigned to transport the molten metal faster, or to avoid sections that are thin enough to solidify before the metal can fill larger cavities beyond them. The last main casting defect is metallurgical casting defects. Metallurgical defects show up when there are problems in the metal of a casting. There are 3 types, which include slag inclusion, hot tears, and hot spots. So, how to prevent metallurgical defects? Can be greatly reduced by using well-designed molds that evenly cool the casting and that deform the proper way in hot conditions. Changing the chemical composition may help to solve the problem. Slag must be removed before pouring of molten metal. As there are so many types of casting defects, it is hard to consider every defect during casting process, so my suggestion is to consider and avoid major casting defects. Thanks for watching. Subscribe for more engineering concepts and happy learning.